Today the workshop is on zero knowledge proofs with Aztec's Noir, and it's a deep dive workshop. So first, I want to make it a bit interactive if that's possible with you guys. So, are you guys familiar with zero knowledge proofs? Can anyone tell me what are the zero knowledge proofs?
It's like a way to cryptographically verify something without needing all the information.
Yeah, kind of. Yeah, you're near the true definition. Yeah. So basically, ZKPs let you prove a secret value without revealing the secret value. So let's say you have a password and you want to prove to a verifying system, or you want to prove to your colleague that you know the password without sharing your password to him. So zero knowledge proofs allow you to do that, uh, in which you don't need to reveal your exact password, which is the secret value here. So there are three components in zero knowledge proof. There is a witness, there is a prover, there is a verifier. So the secret value corresponds to the witness. The prover corresponds to the person claiming to know the witness, and the verifier is the person verifying knowledge of the witness. So we'll get into the details more. So let's take a real world example. So have you played this game? Where's the Waldo puzzle? Does anyone know how to play this game?
Classic.
Yeah, can you tell how can we play this game?
So is it the one where you got Waldo hiding in like a massive crowd and you got to spend like hours just staring at a piece of paper, waiting for him to jump out at you?
Yeah, kind of. So here you can see in Where's the Waldo puzzle, there's a huge picture, and there are lots and lots of people in the picture and lots of things going on. So in this game, there's a huge picture and there are lots of people and lots of things going on. And the goal in this game is to find where is Waldo. So it is like a hidden object game, you can say. Uh, and it's not easy to find Waldo because there are a lot and lots of people. And yeah, so let's say we are playing Where's the Waldo game. And let's say that you found out where the Waldo is. Now, let's say you want to prove to your friend that you know that the exact location of Waldo without giving away the exact location of Waldo. So, I mean, yeah, you have to prove to your friend that you have found Waldo without sharing his exact location. So, how can you do that? Can you tell in practical terms? Let's say you have this piece of paper and you can use any material, any physical material with you. So, how do you think you can solve this puzzle of proving to your friend that you know you have found Waldo without giving away his exact location? So, the hint is that you don't need cryptography here. I'm asking you to use real world material to prove that to him.
So, for example, saying that I walk with Rubinga or Richard.
Sorry, can you repeat that?
Like, for example, saying that Waldo is wearing a red shirt,
Saying that the Waldo
is wearing a red shirt, for example.
no, that's the trait of Waldo. Waldo always wears a red shirt, kind of, in this game.
You said we're allowed pen and paper, right?
Yeah, you have pen and paper. You can maybe use anything that you have at your home.
Could you like draw out like a small section of the image?
Yeah, yeah. So, but if you will draw the section of the image that
Like,
will right to your friend.
like draw directions. Oh, that will reveal the exact location. Okay.
Yeah.
Like if I drew out that small circle there,
Mm-hmm.
this is
Yeah.
another thing.
Yeah.
You could take like a really close picture with your mobile phone, only showing his face, for example.
Yeah, that's possible. That's a good solution. Yeah, I agree with that. So, any more ideas? Because let's say if you take a very close up picture of Waldo and maybe just one or two people near him, so that kind of reveals or that kind of proves that you know the exact location without giving away the exact location. So yeah, you can use your smartphone camera. So um, moving on, let's see other solutions which that have been proposed. So yeah, so this is kind of a bit ridiculous, you can say, because you are directly cutting Waldo and showing it to your friend that you have found Waldo. So maybe the game will not be playable anymore. But yeah, in this way you can prove that you have found Waldo by actually cutting Waldo and showing it to your friend. And the second solution is a more related to the one you had rightly said. So yeah, so the first solution was like cutting it out, cutting Waldo, and directly showing it to a friend that you found him, but the game will not be playable anymore. And the second is more practical, in which you take a sheet of paper which is bigger than the board of Where's the Waldo game, and you place it kind of randomly on the um, Where's the Waldo games board, and you cut out a small hole and you put it on top of the exact place where Waldo is. So let's say the board game behind this is somewhere like this, and you have found Waldo here. So this kind of proves that you have found Waldo, but this will not reveal to your friend that you have, like, the exact location would not be revealed because your friend doesn't know in which part Waldo is currently in, because the board can be like this, or maybe the board can be like this. So maybe in the upper left corner, on the upper right corner, or the lower left corner, it can be anything. So this is similar to how zero knowledge proofs work, in which you are proving to your friend that you know something without actually revealing the exact thing that you know. Okay, so this has a lot of practical solutions in real world life. So some of the examples are, I have a residence in Beverly Hills, but I won't tell you my address. So you're proving that you have residence in a place without revealing your exact address. Uh, then proving that I am eligible to vote, but I won't reveal my identity. So let's say eligible to vote is like you're proving to another person that you are an adult. You pass the minimum age, let's say 21, and you are eligible to vote without revealing your exact age or your identity. Then there are more examples. I am an employee at Coinbase, but I won't reveal my name. I can prove that I received an email from Nasdaq telling me a certain price for a stock, and so on. So yeah, I guess last example is also interesting. I have the right to transfer this ETH, but I won't reveal anything about the history of ownership of these coins. So yeah, private transactions are possible using this. So these are the examples. I'll try to switch back and forth so that I guess this works. Yeah. So moving on to the next slide. There are three properties of the verifier. So this is the kind of formal definition. So there are three properties, and these three properties include the verifier is this verifier in the system, which is verifying the knowledge of the witness. So the three properties are completeness, soundness, and zero knowledge. So completeness means that if the proof is valid, it must be accepted by the verifier. So there is no case in which the proof is invalid and it is, accepted, or if the proof is valid and it is not accepted by the verifier, that does not happen. So if the proof is valid, it must be accepted by the verifier. Pretty basic thing, but really important one. Then soundness. Soundness says that if the proof is invalid, it must be rejected by the verifier. And when you combine these two, you can say that you can trustlessly verify something. And getting to the last one is the zero knowledge, in which the verifier does not learn any information about the witness other than the assertion that the prover knows it. So that's pretty simple, that he does not know. That's the zero knowledge. The only thing he knows is that the prover knows the secret value, and that's it. And no other information is leaked. So that's why we call it zero knowledge, because the verifier has zero knowledge as to what the secret is that the person is having. Going on to the next slide. So what does ZKP solve? So they solve two biggest problems in the blockchains. So one is scalability, so making things smaller and faster to verify, and privacy. So privacy is like, you all know that, keeping data and computations hidden. So they solve these problems, and we have seen a lot of projects like ZK as booming in blockchain. So yeah, going on to the ZKP flow. So the ZKP flow is that the code is first converted into a series of constraints. We will look as to what kind of constraints are these. Right now, you can just think of it like assertions or required statements that the code is having. So these constraints are represented as vectors, and then there is Lagrange interpolation used to convert vectors into polynomials. And polynomials are the ones that let us efficiently check whether two pieces of data are same or not. And that's how we verify whether the person is actually having the secret or not. So this is a high-level overview of how zero-knowledge proofs work. And there is a lot of maths involved in it. So it's out of the scope of this workshop, because it will need a lot of deep diving into that. So we'll mostly be focusing on the code part here. So let me know if you have any doubts related to this. Yeah. So this is the tech stack. So let's say you have a program, you're writing a program in a language, then there's arithmetization of the code, then there's constraint satisfaction. So that's the front end part. So this is the tech stack, that's the front end part, in which there is constraint satisfaction that is being seen. We will look into it via code itself. And this is what happens in the backend, in which there is verifier prover, then the crypto compiler compiles it, and there is some proof system in which you're able to generate and verify the proof. Yeah. So actually there are a lot of proof systems, like there's Halo, there's Star, there's Splunk. So these are very one of the most popular ones. So yeah, do you have any doubt here? This is just a high level overview of how things work. So when you'll be making a zero knowledge proof, let's say a DApp, then I think this would make more sense as to how the things are working in the front end and the back end. So getting into the math a bit. So broadly speaking, a ZK scheme consists of two algorithms. So first, two algorithms are P and V. So you can think of it like prover and verifier, proving and verifying. So the first step is Alice can execute this to generate a proof pi, which she can publish. So F, you can think of it like a function which takes in these values, these variables of x, y, and w. And Bob can then run the verification algorithm, which consists of a function x, y, and pi to verify whether the specified statement is true and that Alice knows some secret such that f of xw is equals to y. So you can see that in the first step, Alice is actually executing this to generate a proof pi, and that pi she can publish because it has like no one can tell about the w, which is the secret, by looking at the pi. And when she publishes this pi, Bob can then run the verification algorithm to verify that that uh, Alice does know something called W without actually knowing the W exactly, such that this is satisfied. F of xw is equals to y. So that's again a high level overview of how the math works in ZKP. So do you have any doubt here? You can interrupt me if you want to ask. Yeah. So you are actually doing like there's on-chain proving and there is on-chain off-chain proving and on-chain verifying, and that's how we unlock the possibility of privacy in blockchains. So there's also third algorithm G, which helps to set up the protocol, but we are not going to see that here, obviously. If you don't have any doubts, I guess then I can move on. Yeah. So the Noir programming language. So Noir programming language is the language of Aztec protocol. So they have built this language. So the two dominant languages to make zero knowledge proof applications were um, ZkComp, and this is the second biggest, you can say, which is Noir. So has anyone known? Does anyone know ZkComp, or has anyone coded in ZkComp before? I hope I'm audible.
Yep, yeah. Just know the name but haven't coded before, yeah.
Okay.
I did some work in CirComp. It's like creating a circuit based on RLCS constraint and all.
Yeah, exactly. So the ZkComp language focuses on um kind of making the circuits uh, which corresponds to the zero knowledge proofs. So you are actually writing uh, complicated circuits in ZkComp language, and the challenging part about it is that there are things that can go wrong while making the circuits, and it's not very developer friendly. So uh, but as opposed to the Noir programming language, you are not actually writing any circuit here. So this is a Rust based language in which this kind of like Rust itself, in which you're writing actual code and not circuits. So it's easier to understand and build on top of this. And it is backend agnostic, and I guess that's also you can also use any front-end language. So yeah, so it's a full and open source, compiled down to any snark-based proving system. You can use any proving system that you like in the backend, and you can use any backend as well. So the Noir Proof generation. So this is kind of the flow here, in which the Noir program is taken by the compiler. It converts it into ACIR, which is this one. You can see, yeah, this part, if I'm not wrong. Then, yeah, ACIR is the abstract intermediate circuit representation. So if you have used ZkComp, then you will be able to understand this part much more easily. Then uh, then it goes to the optimizer, proof backend, and the proof. So that's how Noir proof generation works here. So getting into the layers. So this is the Noir program. There's abstract intermediate circuit representation, which is the ACIR. Then you have backend proving systems like Plonk, Narc, and so on. And each of these have different um, different features based on their uh, cryptographic proofs, and then you can hook this into the Solidity verifier, which is the verifier contract, and you can use any blockchain like Ethereum, Optimism, and so on. So this is how the layers work. And yeah, does anyone have any doubts here? Or I guess we can move on. So yeah, so this is the setup of the Noir language. So I just run Nargo version here. You can see this is 0.31, this version. So Nargo is the terminal, what we say, the command line interface for a Noir language. And there is the setup consists of nargo.toml file, brewer.toml file, and a main.nr file. Okay, so the first thing which I'd like to touch up upon is the finite field arithmetic. So has anyone heard about finite field arithmetics in cryptographic systems? So these finite field arithmetics are so first is the motivation. So why do we need them? So it's because cryptography involves operations on large numbers, and using regular integers will result in overflows, underflows, and various errors. So using finite field arithmetics, what we can do is limit our space to a group of numbers where operations never overflow or underflow. Division results are also in the same group, and memory size is fixed. So this is really important for ZKPs, which involve a lot of mathematical operations in the background, and finite field arithmetics kind of is what makes this practical in real life. So instead of using regular integers, finite field arithmetic is being used here. So yeah, so you can think of it again as like this finite. It goes on from 0 to p minus 1, where p is prime modulus. It's kind of huge prime number, and there's closure. You can do addition, subtraction, multiplication, division, without leaving the field by applying modulus. So you are restricting it in a particular range, and it also follows all the laws of associativity, identity, and commutativity. So there is also multiplicative inverse. So this we'll see at a later point as to how a multiplicative inverse is really important in finite field arithmetics. And yeah, so elements of this field can be integers or elliptic curve points. So you must have obviously heard about elliptic curves, and these fields, the elements of these fields are integers of or points that are corresponding to the elliptic curve points.
I mean, like, can we have some kind of example?
Yeah. So basically, let's directly run the program itself. Okay, I think that will be more that will be more intuitive to understand. So this is the Noir docs, and to give you the example, so the Noir docs, the Noir language right now uses the Grumpkin curve. Okay, so if you want to see how the curve looks like, so we can maybe go to the images here. Okay, there's no such thing here as right now. So basically, yeah, you can think like let's run the program directly. You also call this as baby Jubjab curve, if you have heard about this. And yeah, so here we are importing the standard library. This is the main function, which takes in price, quantity, and cost. So all these three are fields again. And here we are asserting that price into quantity should be equal to cost. So this is actually very similar to integers. Actually, you can just think of it right now as integers, because it works like an integer, as it is constrained between a set of numbers. So the value, you can think that the minimum value is 0 for a field, and the maximum value is a huge number. That's it. And the thing that is restricting these value is just different points on curve, right? So you can just think of it like an integer, but which is constrained between 2 points, two values. Okay, so we will be testing. To test, you write a function called test main, and you write whatever test you want to do. So here we are just calling this function, and this function is asserting whether whatever price quantity has been passed, is their multiplication equals to the cost. So we will run this. Nargo test dash show output. You can see the test is passed. So let's say if I pass the wrong values, what will happen? I should obviously get an error. So you can see the error is fail to solve program cannot satisfy the constraint. So here you can see that these assertions actually correspond to the constraints which we were talking about in this flow. Yeah, constraint satisfaction problem. So the constraints should be satisfied. Otherwise, here you get this error itself. And this is what you can actually use for the front end and that actually helps you to use zero knowledge proof in a practical way. So yeah, you can see the code is first converted into a series of constraints, and here itself, if you give the wrong values, you get here this error of cannot satisfy the constraint. Okay, so that's about it. If you have any doubt, you can ask again. Or I guess if we go to the ZkComp docs, maybe Jubjab curve. So this is the documentation of the ZkComp, and this is again a little bit more mathematical, but but you can see this the mod p which we were talking about. So this you can see is this number, which is a huge number. This one, and that is something that we'll be using for the uh, inverse calculation, so which we will see in a while. Okay, so moving on. If you have any doubt, you can again interrupt me anytime. Yeah, so again, some generic stuff, how the tuples work. So here you can see is the tuple. So I'm right now just copy pasting the code, and tuples are basically you can declare them like this, which has been declared directly in this as a parameter of this function, and you're asserting that the multiplication of the first two items is equals to the third. And again, running this, and it passes. And when I do this, I give it incorrect values, then cannot satisfy constraint again. Pretty simple stuff. Okay. So this you can always find in the documentation, which is pretty good as well. It covers everything. So moving on to the for loop. For loop is it's pretty much like Rust. So here you have price. It has field, and these I guess are arrays. Yeah, and you are running a for loop over this. So arrays are basically declared like this. You can declare an array with a static array with sizes like you are already giving it the values, or otherwise you can declare them like this as well, in which you are specifying the type as field, and this is the size. So this is the syntax of declaring your array. And yeah, you can index it like as always, and yeah, you can use assertions on these elements. So moving on to the for loop. So here you want to loop over this array. So you are just writing for I in 0.2. So I will take the values of 0 and 1, and it will loop over the array of price, quantity, and cost, which all have a size of 2. And it will try to assert that the multiplication of price and quantity should be equals to cost. You can see in the test, we are actually giving these values. We are declaring them and calling the main function and running the test, and it works. And even if one value we give it in correctly, and it fails. So looking at structs is basically, you can see here is the struct item. You are giving them values here. You're declaring its type here, and the elements. So this is price, which is a field. There's a quantity, which is also a field. There's cost, which is also a field. So basically, you must have been having a question again, like does this language support integers or not? So the answer is yes, it does. It does support integers, but there is a reason that we will be using fields instead of these integers. So some of the reasons which I've already discussed here, because cryptography, like, it involves a lot of arithmetics, so it can go run into problems. So fields are what um, we will be preferring. But there's also another reason in which we'll see uh, in the following functions that are yet to come, as to why we will be preferring field over an integer. So one of the reasons is um, yeah, we'll look into it in a while. So yeah, so again, this is a function in which you are um, passing the items, and this is an array of structs, and you're asserting that the price and quantity should be equals to cost. Again, you're declaring them the structs as this. You're running the tests, it passes, and again, I put something wrong, and it will not pass. Yeah, fail constraint. Okay, pretty simple again. So I guess you all can grasp that well. Now moving on to the functions. So functions are you declare them like this, which is basically fn and the function name and what you're passing, here, and what you want to return. You just give an arrow and you just uh, declare the data type of what you want to return, and you just you don't need a return statement. You can directly write what you want to return, and it will return automatically. And this is the syntax of you have declared struct. So basically, uh, this is the implementation of the item, and here you are looping over the items again, and you're trying to check the cost. So basically, instead of asserting in the main function again, which we were doing in the previous example, we have written a function which checks this assertion. So items.check cost, in which this items will be passed, and the self. So it will check that self.price into self.quantity should be equals to cost. So again, declaring the struct, and you are calling this function. Let's see the test pass, and again I'll put something wrong, it will not pass. Again, pretty simple. Yeah, please do ask if you have any doubt. Yeah.
Like, can you give some rough idea regarding how this is being compiled, or like what's happening on the backing side?
Okay, on the backend side, right? So you can see that so I'm deliberately not going in too much into the details, uh, because the math is kind of complex, and it will require a lot of time to cover that. But on a high level, again, uh, what happens is that you are uh, converting this um, into circuits. So as we have talked before, like circomps, which is a zero knowledge proof language, you are just writing circuits. Okay. So the circuits is basically like if the circuit is complete, then you are able to verify that the person is having the secret. And if the circuit is not complete, then then it fails, and you know that the person is not actually having the secret uh, which he's trying to claim he's having. So um, so this works again in a similar way. It's just that it abstracts the complicated stuff that's happening in the backend. So um, this you can think is the constraint in the circuit. So circuit is like it is following a specific uh, specific specific constraints, or you can say limits that this is how the circuit should work. And only when these things are it's following, only then the circuit will complete, and you'll be able to verify uh, the secret value. Otherwise it will not. So that's what we call as I guess here it's the code is converted into a series of constraint. Then you are using vectors. So if you want more in detail, I will give you more resources to go to deep dive into this. So these constraints are represented as vectors. So if you would have studied linear algebra, so you must be knowing like how vectors are working, which is a kind of columns and rows in which you are representing various values. And uh, once these constraints are converted into vectors, then you are converting these vectors into polynomials. And polynomials, so we know that we need polynomials. Why? Because um, you can see here, yeah, you can see that polynomials are being used while proving and verifying, right? So f of x, y, and w, what is that? This is nothing but a polynomial. And again, this is also a polynomial. So the thing is, you want to uh, in the backend, how it works is when these polynomials uh, so ZK is just trying to check whether two pieces of data are same. Okay. And here you can see is that that translates to f of xw is equals to y or not. If this is satisfied, then you say that uh, that you have successfully verified that the person has the secret. Otherwise, uh, he does not have the secret. So that's a high level overview of this. So did you get it? Or
Yep, yep. Yeah, I mean, I got, the overview, but yeah, I'll have to deep dive into it actually.
yeah. So there is a ZkCamp which I've referred for this, obviously. So they do go into a bit more details. So I will link this in the docs, which I will share it with you. And later you can deep dive this into it a bit more. So they have covered a lot of like some maths behind this as well. So moving on, I guess it must be a little bit more clear to you how these things are working. So yeah, right now as a programmer, your job would be to understand how to write a constraint right now. So yeah, sorry, write assertions and things corresponding to that. So here we have seen how the arrays are declared. So yeah, you can also kind of declare an array in this form, in which you are declaring an array of size 32-bit, but all of its elements are initialized as 0. So you can see here that I've declared an array of size 32, and all of its elements have been initialized as 0. Um, we can print some of its values to check here. And pass of 1, so this should work. Yeah, you can see there is this hex values being printed, in which it's showing that these are the 0 values which this cost array is having. So yeah, it's pretty simple. Again, this is how you print again. If you want to print anything to debug, you can use this statement. So yeah, so moving on to declaring array with specific type, you can again, if you want a specific type of array, you can declare it like this. So this is again similar to Rust, if I'm not wrong. And you are, so yeah, let's check again here that we're talking about fields and its values, right? So um, this is again a field array of size 32, but all its values are 0, and you're printing these values. So let's see, and you can see here that again it's a hex value, and it is not very different from what these integer values which we saw. You're seeing this because I had printed 2 values, but again this is again similar to integer values it's taking. So this is how you want, if you want to declare a specific type, you declare it in this way. So now a lambda function. So this is a bit fancy. As you must all obviously know that how lambda functions are there. So here we are basically running this um on this you can see this is a lambda function which you are declaring as to what values you want to pass and what it will do here. So this is a lambda function, and this is basically writing it in a short form as to what it will assert and what it will be returning. And it is just nothing but just calling this function, this lambda function, on all the values of item, and it is doing a check cost, and check cost is nothing but price into quantity should be equals to cost, which we were already doing before this. And basically check cost is returning a boolean value, and if price into quantity is equals to cost, then boolean value will be true, otherwise it will be false. And you can see that this complete will either return true or false. So we are asserting that this should return true for all the items at one go. And yeah, so we will run the test again, and it's passing. So there's this price quantity cost, and you are calling this main function. And you are also, there's also another assert statement here which you can call in the test function, in which we are asserting that the total should be equals to 9. There is something called mutable variables. So to understand that, maybe I should change some of its values. Yeah, let's say I'll take the previous example. I will take the cost of 0 and I will change it to, let's say, 2. And let's see if this works. And yeah. So you can see that in the previous function, uh, I had declared this cost, which was an array of fields. And I'm just trying to reassign the first value to 2. Okay. And here you can see that it just gave me an error that the variable cost must be mutable to be assigned to. So the cost, all the variables by default are immutable variables which you cannot reassign. And if I do it like this, I guess the syntax must be correct. Yeah, it's working now because I just added this mut statement, which is basically telling that cost is a mutable array and you can reassign the values of this array. So right now I am reassigning it to 2 and it's working. But previously it was not working. It was giving this error that the variable cost must be mutable. So here you can see that there's this mutable variable called total, and you are just adding the costs here. Okay, so this is nothing but you're adding the cost and you are checking that the total must be equal to 9. And why 9? Because here the cost is 1, here the cost is 8. And obviously 1 plus 8 should be 9. So we run this and you can see that the test is passing. If I change this to 2, you can see that obviously it will fail because this constraint is failing. And yeah, 1 into 1 is not equals to 2. Let's say if I change it to 2, so 2 into 1 is 2, 2 fours are 8, and now the second constraint is failing, the second assertion, because the total should actually be 10, but I have put it as 9. If I change before moving on to the multiplicative inverse, which is again a bit more technical, I will show you how the verification and proving works so that the picture is complete to you as to what stuff is exactly happening here. So yeah, so this is basically Nodeguardian's tutorial, in which you are basically uh, you have to complete the challenges. So this is a gamified settings in which there are quests and campaigns which you need to complete, and then you'll be able to earn some points. And the quests and campaigns are uh, uh, programming and completing some challenges. So here is a zero knowledge dungeon, there's Hello Noir, and so on. So this is Nodeguardian's tutorial for the Noir. So here basically this actually uses an old version of Noir. So we need a 0.22 version here. So I will be using this version here. So it will download this previous version. Yeah, it has been downloaded. We will go to the hello world. And yeah. So basically here you can see, I guess it should be easier to understand this function. So in our main file, we are declaring a function in which there is key lock1 and lock2, and you are actually we have actually declared it as unsigned integer of size 32, and by default, the key is like a private this parameter, but I guess that's not really important right now. Lock1 is a public variable, uh, again of size unsigned integer 32, and this is again unsigned integer of size 32. And what we are asserting here are simple three statements. The first statement says that the key should not be equals to 1. The second statement says that lock1 should be completely divisible by key, and lock2 uh, should also be completely divisible by the key. So I guess this is, we can call it as GCF if I'm not wrong. Right. So, and we are passing here certain values. Yep. Let's run this. Yeah. So the thing is that, okay, first let's run this test. Nargo test dash show output. Nargo test dash show output. Yeah, the tests are passing. So in the test, I've written 2, 60, and 50. So the key is 2, and lock1, lock2 is 60 and 50. So you can see that's 2 completely divides 60, and 50 is also completely divisible by 2. And similarly, 3 completely divides 6, and 9 is also completely divisible by 3. Now, in this Nodeguardian's challenge, what they are asking is second, I must delete this. And prover.tuml. Okay, so we also need a prover.tuml file, which you can see is not available here right now. So I am creating a prover.tuml file, and this is basically the prover itself, which we were looking in the ZKP. And yeah, so the thing is that everyone knows here that the prover knows that lock1's value is 187, lock2's value is 459, and the thing is, what's the key? Okay, so we need to find the key such that lock1 and lock2 such that it corresponds to lock1 and lock2. And what is lock1 and lock2? They are nothing but this again. So prover.tuml actually just provides value to this function, and key is basically, you can see that here the key is not public. So key is something that is secret here, okay, because that's a private parameter. So when you're passing this, so technically it's a private parameter, and this will not be visible to outside the system, so other people will not be able to know what the key is. And you need to prove that you know the key to these two locks without actually giving your key away. Okay, so that's the challenge here. You need to find the key without actually giving the value of the key. So here what we do is we will do Nargo proof. I will give some random value here. Let's say I don't know if this is correct or not right now. Let's just give a random value. We will run Nargo proof. You can see here that it is failing. The constraint is not being satisfied. Okay, so you can think of this something that happens in the front end, if I'm not wrong. And here, as soon as you're giving an incorrect value, the assertion is failing. Okay, So here what we can do is, as I know the answer, so I'm right now giving the correct answer. So I'm giving the value as 17, which completely divides 187 and 459. And let's now generate the proof. And you can see that proof has been generated. And how the proof looks like. This is how the proof looks like. It's this huge value. Okay. So you can think of this like what we had seen in the slide, which is pi. So we have right now what we have done is we have run the proving algorithm, and we have generated a proof pi, and you can call this complete thing as the pi. So tell me, can you can you backtrack and tell that what's the key value by looking at this huge pi, the proof? Obviously you cannot. So this does not leak any information as to what the key is. Okay. And now let's say that you are publishing this proof, and you are trying to now on the other side, the backend needs to verify whether this whether you actually have the secret value or not, which corresponds to the constraints that this function is having, constraints that the circuit is having. So to do that, we will run a simple nargo verify, and then verify should be empty to verify.tml. Okay, I will delete this for now. Trash. Yeah. So I will do nargo verify. Yeah, I should have not deleted it. Okay. Verifier.eoml and nargo verify. Okay. I guess then uh cannot put it back, but I guess lock 1 was something like this, lock 2 was something like this. Okay, cannot parse from it. Yeah, I guess I just messed something up. Okay, so basically the thing is that these values should have been uh passed as like you're passing the binary values here. I mean in the form of hex, if I'm not wrong. Okay. Yeah, it's working now. So basically what is that the verifier just knows what the values of lock 1 and lock 2 are. And this is nothing but the uh, hex value for lock 1, which is 187. So this is value of 187. If you want, you can also check this in Python. I think this is the syntax, and oops. Okay, we can just run it here. Python 3. Okay. And we are just checking that the values are actually the lock values or not. And I'm just putting this x value here. You can see this is 187. And right now I am putting this second value, and the second value is for 459. Okay. So 187, 459 is what the prover knows as well as the verifier knows. Okay. But the key is something that only you know. And what the verifier is doing is that it is taking this proof and it is running the verification function that corresponds to this constraint, and it is checking whether it is satisfying the constraints or not without actually knowing what the key is. And once you're able to verify it, then then this passes. This silently passes. Does not give any error. If it gives an error, this means that it is not passed. Now the final thing which we'll do is we will generate a Solidity verifier contract using Narboco gen verifier, and it has created this contract, which is a Solidity contract which verifies all the things that's happening here. So this is a huge contract, but what's important for us is this part, which is verifying the verification function, which helps us verify on the blockchain whether the key corresponds to, like, satisfies the constraint or not. And if we want, we can run this in our contract here. So let's try to run this and see if it works. It gives stack to deep error. Okay, so we can just enable optimization, and it passes. And I'm trying to deploy. So that's an abstract contract. I guess that's an ultra verifier contract. Okay, that's ultra verifier contract. I am deploying this, and yeah, you can see this is get verification hash. It's a verification hash, which actually is nothing but the hash of this ultra verification key contract, if I'm not wrong. And the load verification key is basically verifying the stuff on a blockchain. So this is the verify function. Okay, here we if we put the proof, which is the public proof, and we put the public inputs is lock 1 and lock 2 here, then we will be able to verify on the blockchain whether this proof corresponds to the public inputs and the circuit generated or not. So basically, again, whether Alice actually have the secret or not, the secret key or not, this verify function verifies. So let's try to run this. So I already have this. So proof is this is the public inputs, which is lock 1 and lock 2, which I have pasted here, which we know is 187 and 459. And the proof is basically this complete proof, which we had generated. And I'm just copying this and I'm pasting here. And oops, yeah, I call the verifier and it just got errored. Okay, I guess I should be giving this 0 that's this way. Okay, you can see that the verify function passes. Okay, and uh, if even let's say the proof is something else, so instead of 6 I am putting it as 9, and I'm calling this, and you can see that this gives an error, and the error would always be this out of gas error. But if the proof uh, is what corresponds to the value of 17 here, which is the key value, so if I put the correct proof, the verifier passes. Okay, so do you have any doubts here? You can ask, and I guess we are pretty much over the limit here. Uh,
Does verifier like run those asset statements on like key 1 and key 2? I mean, like from the proof, is it somehow calculating 17 and then dividing 189 and the other value and checking like 0?
Can you repeat your question again? I think you're trying to ask that does verifier know about like
Yeah, I'm just trying to understand, like, we have the proof, and until we know the key value, right? How we are going to run those asset statements, right? Divide the numbers by 17 and then know if it's like completely divisible or not.
um sorry, but I still didn't get the question. Can you ask again?
Um, okay, I'll ask later. Yeah.
Okay, yeah, sure. Yeah. So just like as per my understanding, uh the solidity contract that has been generated is basically is having uh a way in which you are running this verification function. Okay, and you can see that the verification algorithm here takes a pi, takes these values, public inputs, and it tries to check whether the things are being satisfied or not. So here the this is automatically generated by the Nargo CLI itself, and yeah, maybe you can deep dive into this a bit more, or maybe looking at the comments, and yeah, I guess that's again arithmetics and stuff that's happening in the backend. Yeah. Mm. So I guess that's it. So maybe we will cover some of the things later, because I guess it would be too much for today. There are just a couple of things, but by the time I can give you this Nodeguardians campaign, which you can practice upon, and you can, yeah, brush up, because this is like a very fun gamified way to understand stuff that's happening. And this zero knowledge dungeon is like uh this is one of my favorite quests, in which basically you want, there's a chessboard and there is a dagger somewhere, and there is a knight on the chess, and you need to prove that the initial position of the knight and the paths, which is a public input, is that reaching to the dagger or not. So the path would be a public input, and I guess um, what's secret is the dagger's position, if I'm not wrong. And this is maybe like a game in which there's a hidden chest, and you're trying to move along the map, and if you have the correct path, you are able to land on the place and you get the treasure chest when you land correctly. So it's like you are just on the initial place, and you are giving the path to the treasure chest, and you're just checking beforehand that whether this path is like following the knight's move correctly or not, and is it landing on the treasure chest or not. I guess that's it.